And welcome back. As we continue our cosmic journey, let's go ahead now and wrap a lot of our things that we've talked about with galaxies up to really summarize the formation and evolution of galaxies. So let's start this off by really recapping how galaxies form and grow. We've already seen that galaxies were more numerous but smaller, bluer, and clumpier in the distant past than they are today, and that galaxy mergers actually play a very significant role in their evolution. Quasars and galaxies emitted the light when the universe was less than 1 billion years old, and many quasars are found in the centers of elliptical galaxies, which means that some of the first large concentrations of matter must have evolved, therefore, into elliptical galaxies. The supermassive black holes that we find in the center of galaxies and the spherical distribution of ordinary matter around them must have formed at the same time and through related physical processes. This means there have been two main types of galaxy formation models to explain these observations. The first asserts that massive elliptical galaxies formed in single rapid collapse of gas and dark matter, during which virtually all the gas was turned quickly into stars. Afterward, the galaxies changed only slowly as the stars evolved into this top-down scenario. The second model suggests that today's giant ellipticals were formed mostly through mergers of smaller galaxies that already converted at least some of their gas into stars. Now, astronomers have debated whether giant ellipticals that form most of the stars in the large galaxies that we see today, or in separate smaller galaxies that subsequently merged into this kind of bottom-up scenario. Now, we've seen some luminous quasars from when the universe was less than 1 billion years old. So we know that at least some of the giant ellipticals began their evolution very early on through the collapse of a single cloud. Now, the best evidence also seems to show that the mature giant elliptical galaxies, like the ones we see nearby, were relatively rare before the universe was about 6 billion years old, and that they are much more common today than when they were when the universe was young. Now, observations also indicate that most of the gas in elliptical galaxies was converted into stars by the time the universe was about 3 billion years old. So it appears that elliptical galaxies had not formed many new stars since then. You'll also hear that elliptical galaxies are said to be red and dead, which means that they contain mostly old, cool red stars, and there's little to no new star formation actually ongoing. Now, the situation with spiral galaxies is apparently very different. The bulges of these galaxies formed very early, much like elliptical galaxies. The disks formed later. Remember that the stars in the disk of the Milky Way, for example, are much younger than we see the stars in the bulge and the halo. And these still contain gas and dust. However, the rate of star formation in spirals today is about 10 times lower than it was 8 billion years ago. Now, the number of stars being formed does drop as the gas is used up. Spirals seem to form mostly using the bottom-up scenario, but they do this over a longer period of time than ellipticals, and they do so in a more complex way with at least two distinct phases. So let's zoom out now and talk about the galaxy clusters, the superclusters, the voids, and the filaments. How do these form? Well, if individual galaxies can seem to grow by assembling smaller pieces together gravitationally over cosmic time, what about the clusters of galaxies we see, or even some of the larger structures? How do we explain the large-scale maps that show galaxies distributed on the walls of these huge sponge or bubble-like structures, those filaments that we see spanning hundreds of millions of light years? Well, observations have found increasing evidence for concentrations, filaments, clusters, and supercluster galaxies when the universe was less than 3 billion years old. Prior to that, these structures didn't really quite exist. This means also that large concentrations of galaxies had already come together when the universe was less than a quarter as old as it is now. And almost all the currently favored models of how large-scale structures formed in the universe tells a story very similar to that of individual galaxies. Tiny dark matter seeds in the hot cosmic soup soon after the Big Bang grew by gravity into larger and larger structures as cosmic time ticked on. The final models we construct will need to be able to explain the size, shape, age, number, and spatial distribution of galaxies, clusters, and filaments. Not only today, though, but also farther back in time. So astronomers are working very hard to be able to measure and then model these features of large-scale structures as accurately as possible. So far, a mixture of about 5% normal atoms, 27% cold dark matter, and 68% dark energy seems to be the best way to explain all the evidence we currently have available. Now, scientists even have a model to explain how a nearly uniform hot soup of particles and energy at the beginning of time acquired the kind of Swiss-like cheese structure that we now see on the largest scales when we start looking at these filaments and voids. When the universe was only a few 100,000 years old, everything was at a temperature of a few thousand degrees. And theory suggests that at that early time, all the hot gas that was present in the universe was vibrating, much as how sound waves vibrate the air of a nightclub when it's especially loud band. This vibrating could have then concentrated matter into high-density peaks and created emptier spaces between them. When the universe cooled, the concentrations of matter were then frozen in, and galaxies ultimately formed from the matter in these high-density regions. So what's our big picture? Well, initially the distribution of matter, both luminous and dark, was nearly but not quite exactly smooth and uniform. Here and there were lumps where the density of matter, both luminous and dark, was ever so slightly higher than average. Now each individual lump then expanded because the universe as a whole was expanding. However, as the universe continued to expand, the regions of higher density acquired still more mass because they exerted a slightly larger than average gravitational force on surrounding material. If the inward pull of gravity was high enough, the denser individual regions ultimately stopped expanding. They then began to collapse into irregularly shaped blobs. In many regions, the collapse was more rapid in one direction, so the concentration of matter were not necessarily spherical, but instead came to resemble giant clumps and rope-like filaments. And so this image that we can look at here really kind of shows the train wreck of chaotic galaxy shapes and blue tidal tails nearly 10 billion years ago. So this is very early after the formation of most things that we kind of start seeing for our universe. In here we can see there are several galaxies right in the core that are merging, and the probable cause of a massive burst of star formation and bright infrared emission from the cluster. Now, the elongated lumps that we talked about existed throughout the early universe, oriented in different directions and collapsing at different rates. These clumps then provide the framework for large-scale filamentary bubble-like structures that we see preserved in the universe today. Within these clumps, smaller structures form first, then merge to build larger ones. First, dense concentrations of matter that collapse were the size of small dwarf galaxies or globular clusters, and these fragments then gradually assembled to build galaxies, galaxy clusters, and ultimately superclusters of galaxies. And this image really kind of gives a good representation of how the filaments and superclusters of galaxies grow over time, from a relatively smooth distribution of dark matter and gas, with only a few galaxies formed in the first 2 billion years after the Big Bang, to the very clumpy strings of galaxies with large voids today. Now, keep in mind that most giant elliptical galaxies form through the collision and merger of many smaller fragments. Some spiral galaxies may have formed in relatively isolated regions from a single cloud of gas that collapsed to make a flattened disk, but others acquired additional stars, gas, and dark matter through collisions, and the stars acquired through these collisions now populate their halos and bulges. And this diagram shows how galaxies might have formed if small clouds formed first, and then congregated to form galaxies in the clusters of galaxies. You see we first kind of start off with some small clouds that were kind of gravitationally attracted toward each other. These then came to form galaxies. In this particular image, we're looking at a spiral galaxy. And then, of course, those different effects of gravity are going to pull those galaxies toward each other, and then we are forming now a cluster of galaxies.